Okay, let's dive into this. Welcome, first semester BCA students, to today's Explainer. If you are staring down your discrete structure syllabus right now and wondering exactly how all these numbers and brackets are going to fit into your future as a software engineer or a data scientist, well, you are in the exact right place. Today, we are completely unpacking Unit 3 matrices. But listen, we aren't just going to look at them as dry, boring math problems. We're going to look at them for what they truly are, which is the absolute essential data toolkit for any data architect. Here is our quick roadmap for today's upgrade path. We'll kick things off with an intro to matrices and their types, then we'll cover operations and determinants. After that, we'll tackle inverses and solving linear equations, break down some eigenconcepts, and finally tie the whole shebang back to your computer science applications. Let's get to it. All right, part 1, Introduction to Matrices and Types. Before we can start building complex algorithms, we really need to understand the raw materials in our toolkit. I want you to imagine floating numbers snapping perfectly into a highly structured, bracketed grid. That right there is a matrix. In computer science, structure is literally everything. We define a matrix by its order, which is simply the number of horizontal rows followed by the number of vertical columns. So an m by n matrix just means it has m rows and n columns. It's essentially a meticulously organized two-dimensional array of data just waiting to be processed. Now, your syllabus specifically requires you to recognize a few special configurations. First up is the square matrix. That's where the number of rows perfectly equals the columns. Think of your classic 2x2 or 3x3 grids. Then we have the diagonal matrix, which is a square matrix where all the action happens right on the main diagonal, from top left down to bottom right, and absolutely everything else is 0. Take that a step further, and you get a scalar matrix. And finally, there's the identity matrix, where that main diagonal is made entirely of ones. And a brilliant illustration of exactly what you might see on your exams is a 3x3 scalar matrix. In fact, a recent model question paper specifically asked to define a scalar matrix with an example. For a 3x3 version, you'd have the exact same number, let's say the number 3, running all the way down that main diagonal, while every single other element is a 0. It's basically a diagonal matrix where all diagonal elements are perfectly equal. Master that visual, and you've secured those exam marks for sure. Moving right along to Section 2, Matrix Operations and Determinants. Now that we've identified our materials, let's figure out how to actually wield these tools to transform our data. The most basic operations you'll run into are addition and subtraction. Honestly, just think of this as taking two identically sized grids and sliding them together so that every corresponding element adds or subtracts. It's a direct one-to-one mapping. Scalar multiplication on the flip side is when you take a single standalone number, a scalar, and multiply it by every single element inside that matrix grid. This effectively scales your entire data structure up or down uniformly. But then, we get to matrix multiplication, which definitely requires a bit more mental gymnastics. This isn't just a simple slide and combine. I really want you to visualize a row-by-column dive. First, always check your dimensions. The column count of your first matrix absolutely must match the row count of your second. If they match, you're good to go. You take a row from the first matrix, dive it down a column of the second matrix, multiply the corresponding elements, and then add those products together to create one single new element. It's a highly rhythmic, almost algorithmic action. Let's ground this theory in a real exam scenario taken straight from a model paper. Imagine we have a 2x2 matrix A multiplied by a 2x2 matrix B. Let's mentally trace that first element. We take the first row of A, which is 2 and 3, and dive it into the first column of B, which is 1 and -1. We multiply 2 by 1 and 3 by -1, add them up, and get 2 minus 3, which equals -1. That exact process repeats for every single row and column combination, building out our final resulting matrix. Let's pivot and see how this builds into our next core concept, the determinant. The determinant is this special, unique scalar value that we can calculate, but only from a square matrix. You can think of it almost like a DNA test for the matrix. It tells us crucial properties about the system, most notably whether the matrix can be inverted or not. If your determinant turns out to be 0, that matrix is basically a dead end for certain types of advanced operations. Now, what's really interesting about calculating a 3x3 determinant, like the ones you'll see on your model question papers, is that you have to find what are called the minors. This involves picking a specific element, let's say the number 1 in the top left corner, mentally crossing out its entire row and its entire column, and looking at the smaller 2x2 matrix that's left behind. Calculating the determinants of those smaller leftover blocks is exactly how we solve the larger puzzle. On to Section 3, Inverses and Solving Linear Equations. With our operations and determinants firmly in our tool belt, we are ready to start building real structures and solving complex systems. In computer science, we often need to reverse a matrix operation, which means finding its inverse. Imagine a matrix actively transforming some data, and then the inverse matrix acting like a rewind button, perfectly undoing that exact transformation. To find it, you follow 3 strict algorithmic steps. First, calculate the determinant, and remember, it absolutely cannot be 0. Second, find the adjoint matrix, which involves calculating all your cofactors and transposing them. Finally, just multiply that adjoint matrix by 1 over your determinant. And a quick heads up, your syllabus places a really heavy emphasis on proving these concepts. A classic model paper question asks you to verify that the inverse of the product of 2 matrices, A and B, is equal to the product of their inverses, but in reverse order. So the inverse of AB equals the inverse of B times the inverse of A. It's a beautifully symmetrical property that pops up in exams all the time, so you definitely want to practice calculating both sides to prove they match. So what does this all mean? Why do we do all this? Well, one major reason is solving systems of linear equations. Enter Cramer's rule. This is a highly mechanical, step-by-step method that you're going to love. You convert your equations into a matrix format. You find your main determinant, D. Then you selectively swap out columns of your matrix with your result vector to find brand new determinants, dx, dy, and dz. Finally, simple division gives you your x, y, and z variables. It's pure, applied, beautiful logic. Section 4, Eigenvalues and Eigenvectors. This is where we unlock the most advanced computational properties of matrices in your entire syllabus. I want you to picture a graph in your head with a vector arrow pointing in a very specific direction. Usually, when you multiply that vector by a matrix, the arrow gets stretched and it gets rotated. It ends up pointing somewhere entirely new. But what happens when a specific matrix transformation stretches the arrow but leaves its core direction completely unchanged? That phenomenon is exactly what eigenvalues and eigenvectors are all about, conceptually, and without getting bogged down in the really complex proofs just yet. The eigenvector is that special, stubborn arrow that completely refuses to rotate when the matrix acts on it. It just scales. And the eigenvalue? That is simply the scaling factor. It's just a measure of how much that specific arrow was stretched or shrunk. Understanding this behavior is absolutely fundamental for optimizing algorithms and understanding data variance later in your career. All right, Section 5, Conclusion and CS Applications. We need to summarize this awesome toolkit and connect it directly to the lab work you are doing right now in your degree. Let's do a fast-paced recap of what we've achieved. You've now got a rock-solid conceptual grasp on the different types of matrices. You know how to execute that row-by-column die for operations. You understand the DNA test of determinants, how to build inverses, how to run the Cramer's rule algorithm, and you even know the directional magic of eigenconcepts. And honestly, this isn't just abstract theory. If we think about the official course outcomes mandated by the Bangalore University syllabus, mastering these exact matrix operations is explicitly required to address real-life problem solving. You are now perfectly aligned with exactly what the university expects you to execute on your exam. But you know, the real magic happens when you sit down at your keyboard. Your problem-solving labs require you to write C and Java programs that utilize single and multidimensional arrays. You are literally going to be writing the code to execute matrix addition, subtraction, and multiplication algorithms. The math we just covered today, that is the exact blueprint for the logic you will code in your lab sessions. You simply can't write the loop if you don't understand the row-by-column dive. And looking a little further ahead to your future classes in AI and machine learning, matrices are exactly how we represent massive data sets. They are how we rotate 3D objects in computer graphics. They are the absolute backbone of neural networks. So the next time you look at a supposedly boring grid of numbers in your discrete structures textbook, I want you to ask yourself, is this just math? Or is this the matrix waiting to build the next generation of AI? Thank you so much for joining me for this explainer, and best of luck in your exams and in your coding labs.